There is a size where gravity simply gives up now. Past that size, expansion wins and structures stop growing forever. The immediate takeaway is that space itself picks the winners. Galaxies, clusters, and even planets live under that rule today. We will watch gravity arm wrestle the expanding fabric of space. By the end, you will see who actually survives here. Night sky spread over a quiet desert. Stars slide apart slowly. Astronomers call the tipping line the turnaround radius, where expansion stalls locally. It matters because that line decides whether a group stays together. Gravity tugs inward while the Hubble flow pushes galaxies apart like a tide. A dense patch pulls harder than average so it can peel off. Once detached, that patch collapses, heats, and settles into a bound system. If it never detaches, it stretches thinner and never fully forms. Rule of thumb, if gravity beats expansion at that edge, it wins. The local group sits on the winning side across a few million light years. Andromeda is heading toward us, about 100 kilometers per second. Distant dwarfs outside that line already drift with the general expansion. Telescopes map that boundary by tracing infalling velocities around the group. Models predict a similar boundary around clusters, near a few megaparsecs. Cross that line inward and galaxies turn around toward the center. Cross it outward and they join the cosmic flow again. This line moves over time, shrinking as dark energy takes over. Net result, the turnaround radius draws the border between islands and ocean. A star skims a warped path near a massive galaxy's heart. Curved space means straightest possible paths bend, even with no forces. That matters because geometry decides how gravity focuses or spreads influence. In general relativity, mass tells space to curve and space guides motion. Near mass, nearby paths converge, while far paths stay almost parallel. Global curvature across the universe stays near flat from precise measurements. Yet local curvature around black holes and stars sculpts orbits and tides. Light also curves, so lensed arcs reveal invisible mass along sightlines. Around Sagittarius A star, stellar orbits precess slightly with each close pass. That precession matches relativity, measured over years with exquisite precision. Mercury's orbit precesses too, by 43 arcseconds per century. Galaxy clusters lens background galaxies into stretched banana shapes, exposing hidden dark halos. The mechanism is simple to picture, though the math runs deep. Objects follow geodesics, which are space's straight lines inside a curve. Space curvature changes those geodesics, so paths tilt toward dense regions. One sentence recap: geometry sets the routes that structure must follow. Cold gas drifts through a dim nebula, then knots begin forming. The threshold that separates collapse from dispersion is called the gene's length. You care about this because it selects which clouds birth stars. Inside a cloud, pressure pushes outward, while gravity tries to pull inward. If the cloud cools, pressure drops and gravity gains the advantage. If sound moves slowly, ripples cannot support the gas against gravity. Regions larger than the threshold collapse, while smaller regions wash out. Chemistry helps too, because molecules radiate heat away and speed collapse. Dust grains shield cores from starlight, letting temperatures drop even further. Example in real terms, a 50 light-year cloud can fragment quickly. A 5 light-year cloud that stays warm may resist collapse. Observers clock collapse times near 1,000,000 years for large clouds. Fractions of 1,000,000 years pass between the first and second generation. Star clusters then light up feedback that halts further collapse nearby. Supernovae stir the gas and reset the threshold for the region. So the picture is, temperature and size decide which knots survive. Picture a dark theater of numbers behind the night sky's glow. Cosmology runs on a few parameters that steer growth and fate. H0 sets expansion speed now and calibrates distances across space. Omega matter sets average matter density, and omega lambda sets acceleration. Sigma 8 sets clump strength on 8 megaparsec scales at present. These matter because they predict how fast structures grow, then stall. When acceleration dominates, new mergers slow and edges freeze in place. Growth factors calculated from those values match observed clustering across surveys. Patterns in galaxy maps align with models that use Planck values. Cluster counts over redshift follow the same tuned parameters within errors. Weak lensing cross checks the numbers with independent distortions of shapes. The ensemble points to a near-flat universe with late acceleration. Tiny tests change sigma 8 slightly and cluster numbers swing. Shift H0 and every derived distance shifts as well. tweak omega matter, and the growth history tilts noticeably. The takeaway is simple: a handful of numbers sets the script. A fragile dwarf galaxy trails stars like smoke behind a cruiser. Astronomers mark the outer edge by a feature called Splashback. That boundary matters because it separates first-time infall from settled members. Material falls in, swings past the center, then reaches a far turning point. It slows there, and that slowdown piles matter into a faint edge. Faster recent growth pushes the boundary outward, while quiet growth pulls inward. Galaxies carry histories in those outskirts, like rings inside tree trunks. Observers map the edge by stacking many halos statistically in surveys. Lensing strengthens right near the edge, confirming the pileup of material. Around Milky Way-sized halos, that radius sits near 300 kiloparsecs. In fat clusters, it can push near 2 megaparsecs across. Streams of shredded dwarfs often light up the zone dramatically. Satellites cross the edge, then mix and phase wrap into shells. Gas follows similar arcs, cooling where orbits briefly linger at apocenter. Common mistake is thinking halos end where starlight fades to black. Bottom line, growth leaves fingerprints, and Splashback is the readable rim. A bruised moon passes a striped giant, cracks glowing with stress. Tidal gravity is the difference in pull between near and far sides. That difference matters because it can unbind rocks or squeeze oceans. Closer orbits feel stronger gradients, while distant orbits feel mild stretching. Inside a critical distance, material cannot hold itself together against tides. That limit is the Roche limit, set by density and size. Soft bodies cross it and become rings like rubble in a blender. Rigid bodies can pass closer, but fractures still propagate through crusts. Heat also flows as tides need interiors, feeding volcanoes and geysers. Io blazes with lava because Jupiter twists it every orbit. Comet Shoemaker, Levy 9 broke apart before slamming Jupiter in pieces. Dwarf galaxies grow tidal tails when skimming massive galaxies during passes. Those tails mark gravitational fields like chalk dust tracing swirling air. Example in numbers, Saturn's rings sit well within that limit. Many small moons survive because they orbit just outside the boundary. What to remember: tides decide who shreds, who warms, and who lasts. A lonely galaxy floats in an enormous void, stars thinning outward. A void is an underdense region where expansion runs slightly faster. You care because location decides the far future of each galaxy. Where density is high, gravity binds an island that resists expansion. Where density is low, space stretches matter into thinner and thinner filaments. Dark energy amplifies this split, accelerating separation on very large scales. Bound regions still merge internally, but their borders freeze against the outside. Eventually, only islands remain, each wrapped by a quiet event horizon. In our neighborhood, the Milky Way will merge with Andromeda soon. The pair will form a single giant elliptical in several billion years. Farther out, Virgo will still exist, but its outskirts grow quieter. In 100 billion years, unbound galaxies slip beyond our observable reach. Their light redshifts so far that even infrared detectors fail. One sentence recap: the universe keeps what is bound and sheds everything else. A razor-thin disk glows around a black hole, jet-spearing night. The sphere of influence is where a black hole's gravity dominates. That boundary matters because it sets which stars feel direct control. Inside, orbits reflect the central mass, while outside, the galaxy takes over. Stars scatter into lost cones, and some dive toward tidal shredding. Heated gas spirals inward, feeding flares and launching collimated jets outward. Those jets slam halo gas, pressurize it, and throttle future star formation. Astronomers estimate this sphere using stellar speeds and measured stellar densities. In the Milky Way, the boundary spans a few parsecs across. Mate 7's monster rules a region thousands of light-years long via jets. The Event Horizon Telescope imaged its shadow, outlining spacetime's tightest bend. Nearby stars whirl around Sagittarius A star with decade-scale periods. Their motions reveal the central mass within a few light hours. So the picture is, a compact center can govern a huge neighborhood. We started with a hard claim and then followed the evidence. Space decides which structures grow, which stall, and which fade away. Islands win where gravity rules, while oceans claim everything else. You now know the borders, the telltales, and the future map. If this cosmic playbook sparked ideas, share it with one friend. Thanks for hanging out under the stars tonight, and come back soon.